So let's look at example 6 here again, testing for continuity. This first problem is a problem that we've done twice already, essentially. It says, find the intervals of continuity for f of x equals tangent of x. And we just did this on the previous page. Remember that tangent of x is sine of x over cosine of x. It is a fraction. And so we know that cosine of x cannot equal 0. So we think about when is x or cosine of x equal to 0, and that's x equals k pi over 2 for any odd integers k. Odd integer k, I'm writing that. So that's what x cannot equal, is any k pi over 2 where k is an odd integer, where that's pi over 2, m pi over 2, or sorry, pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. If you look in the book, they have it written a little bit differently. They have x cannot equal pi over 2 plus n pi, and then here they have n as any integer. Okay, and it's the exact same thing, just written a different way. I said odd integers, they say integers, but it doesn't matter. That's not what they asked here. That's where is it undefined? We want to find the intervals of continuity, so this is where we did the, well, it was negative 3 pi over 2 to negative pi over 2. It was the negative pi over 2 to pi over 2. And then it was pi over 2 to 3 pi over 2. And so on. So that's all your odd integers. So that's the intervals of continuity. It's really easier to talk about when is it discontinuous than when is it continuous on some problems like these. Most likely when you get into WebAssign or whatever your online homework system is when you're doing this is going to be a multiple choice problem, and you'd be able to select the proper answers right there. It would either be the first one saying where is it discontinuous, or B, they would give you options of selecting the proper intervals. So look for that, okay? The next function we need to look for is what is sine of 1 over x. When would that function be continuous? Well, we know sine of x is continuous, or sine of anything is continuous, negative infinity to infinity. The problem here being that x equals 0 is our issue, okay? So we need to consider what happens as x approaches 0. So what's the limit as x approaches 0 of sine of 1 over x? And just think about what's the actual function value. So what would happen here? Well, if you remember, we're actually revisiting this problem. If you remember what the graph looked like, this is the graph that oscillated and got infinitely oscillated close to there, but we said the limit didn't exist because at 0 it infinitely bounced between values of -1 and 1. So there was actually nothing that we could do there in terms of the limit. So it didn't approach a single value. So when we define it, so even though we define it at the point 0 when x equals 0, it still can't meet and be at that one point, so it wouldn't be continuous at that point. We know that it's continuous on the interval negative infinity to 0. We know it's continuous on the interval 0 to infinity. The question is it continuous at 0? And the answer is no. So this would be the answer right here, negative infinity to 0 and 0 to infinity. Let's continue on to the next one. This one's very, very similar, except it's a little bit different because we have this new x in front here. And that makes all the difference in the world. If you looked at the graph on this one, instead of oscillating infinitely, which it still does, it actually dampens and it gets smaller and smaller and actually approaches 0 and then goes back to bigger and bigger. So it actually, the y values do approach 0. They don't oscillate between -1 and 1. They get smaller and smaller and actually approach the value 0. And there's a real easy way to do this as well. What you could do is look and say this is bound by this sine of 1 over x. We know that's always a value between -1 and 1. So x sine of x is bounded by the absolute value of x from above and negative the absolute value of x from below. Let me go ahead and undo that real quick. Negative the absolute value of x below and the absolute value of x above. And let me show you what that looks like graphically. Well, look at this graph right here. This would be the graph of absolute value of x. This right here would be the graph of the absolute value of the negative absolute value of x. And so actually what you could do is say every single value of sine of x, x sine of 1 over x is less than the absolute value of x. It's also greater than negative the absolute value of x. And if you notice, the limit of absolute value of x as x approaches 0 for both of those is 0. So essentially, we just did an example of the squeeze theorem. We found something above that goes to 0, something below that goes to 0, so we know that that middle function must actually go to 0. So we know the limit goes to 0. The function is defined at 0. So since the limit exists and the function exists and they're the same thing, we know it's continuous at that point. Again, this first function is continuous absolutely everywhere except possibly at 0, but because it's a piecewise defined function and defined at 0, it's also continuous at 0. So what does that mean we could do for the intervals of continuity? We could say that the answer is negative infinity to infinity. On this one, we're actually able to include the point 0 because the limit exists, the function exists, and they're the same thing at 0.